The unexpected object. For decades, humanity has learned to predict the sky. We track asteroids, we calculate trajectories, we simulate impacts decades in advance. The universe, at least within our solar system, has become something we believe we understand. And then, objects like 3I Atlas appear. Quietly, without warning, without slowing down. 3I Atlas was not discovered because it behaved normally. It was discovered because it didn't. While most interstellar objects lose speed as they interact with solar gravity, radiation pressure, and internal outgassing, 3I Atlas did something unexpected. It kept going. Not accelerating dramatically, not braking, but refusing to slow down in ways our current models predicted it should. At first, astronomers assumed the explanation would be simple: a miscalculation, instrument error, incomplete data. That is usually how these stories end. But this time, the data did not resolve the mystery, it deepened it. When higher resolution images began to arrive, they revealed something subtle but unsettling. 3I Atlas did not behave like a typical comet. It did not behave like a typical asteroid. And most importantly, it did not behave like an object that had spent billions of years traveling passively through interstellar space. This is not the first time an interstellar visitor has surprised us, but it may be the first time we are forced to confront how incomplete our assumptions truly are. To understand why 3I Atlas matters, we must step back. We must understand what scientists expect to see and why this object quietly violated those expectations. What should have happened? When an object enters the solar system from interstellar space, physics is unforgiving. Gravity pulls, radiation pushes, thermal stress fractures surfaces, volatile materials evaporate. Over time, motion changes, speed shifts. Even the most inert objects show signs of interaction. This is not theory. It is observation repeated thousands of times. And yet, 3I Atlas appeared almost indifferent to these forces. Initial trajectory models predicted a gradual deceleration as the object moved deeper into the solar environment. But follow-up observations showed something else. The speed curve flattened. Not abruptly, not dramatically, but persistently. As if something subtle was counteracting forces that should have slowed it down. At this point, the question was no longer, what is 3I Atlas made of? It became, what assumptions are we making about interstellar objects that may no longer hold? The new HQ images. As larger telescopes focused their attention, the quality of the data improved. Sharper contours, more precise brightness measurements, better thermal estimates, and with clarity came discomfort. The object's surface reflectivity did not match typical cometary ice. Its thermal signature did not align with simple rocky bodies, and its lack of visible outgassing raised a troubling question. If it wasn't expelling material, what was balancing the forces acting upon it? Some researchers suggested that we were witnessing an unfamiliar form of outgassing. Others proposed that the object's shape might be far more extreme than originally assumed. A thin geometry, a strange orientation, anomalous rotation. Each explanation worked, but only partially. None resolved all anomalies at once. And this is where the story becomes more interesting. Because in science, when multiple explanations fail to fully converge, it is often not the data that is wrong, it is the framework. the dangerous comfort of familiarity. Human understanding relies on categories: asteroid, comet, interstellar debris. We label objects so we can predict them, but the universe does not care about our labels. 3-Eye Atlas is forcing scientists to confront a possibility that is uncomfortable but necessary: that interstellar space may be producing objects far more diverse than our solar system-born expectations allow. This does not imply anything extraordinary. It does not imply intelligence. It does not imply intent. But it does imply ignorance. And that may be more unsettling. Because if 3-Eye Atlas is not slowing down for reasons we cannot fully explain, then it suggests something deeper: that interstellar space is not simply a graveyard of debris, but a dynamic environment capable of shaping matter in ways we are only beginning to observe. A quiet warning. The universe rarely announces its mysteries loudly. Most revelations arrive quietly, incrementally, almost politely. 3-Eye Atlas does not scream anomaly. It whispers it. Through subtle deviations, through persistent inconsistency, through data that refuses to align perfectly. And that is precisely what makes it dangerous to ignore. Because history shows us something important. Every time astronomy assumed it had the full picture, the universe revealed how small that picture truly was. In the next part, we will examine what specific anomalies in motion, structure, and thermal behavior are causing scientists to reconsider what 3-Eye Atlas might actually be. Not speculation, not sensationalism, just physics meeting its own limits. In the first part of this analysis, we established one simple but unsettling fact. Object 3-Eye Atlas is not behaving the way known celestial objects usually do. Its trajectory is unusual, its velocity is unusual, and now, with the release of new high-resolution images, its physical characteristics are becoming even more difficult to explain. This is where the mystery deepens, because motion can sometimes be misleading, but structure rarely lies. A closer look at the images. When astronomers first detected 3-Eye Atlas, the data was limited. Low resolution, sparse light curves, basic trajectory models. At that stage, it was still reasonable to assume that 3-Eye Atlas was simply another interstellar object, perhaps similar to Oumuamua or 2-Eye Borisov. But as higher quality images began to arrive, that assumption started to weaken. The object did not resolve into a classic comet shape. There was no clear coma, no extended tail, no obvious outgassing plume that would explain its brightness. Instead, what scientists observed was something far more ambiguous: anomalous brightness patterns. One of the first red flags came from the brightness measurements. Normally, as an object approaches the sun, its brightness changes predictably. Comets brighten as volatile materials vaporize. Asteroids reflect sunlight based on surface composition and rotation. 3-Eye Atlas does neither cleanly. Its brightness fluctuates, but not in a way that matches known models. At times, the object appears brighter than expected. At other times, it dims without a clear cause. This suggests one of two possibilities. Either the surface properties of 3-Eye Atlas are unlike anything we've cataloged before, or its orientation relative to Earth is changing in a non-standard way. Both options raise questions. Shape without certainty. High-resolution imaging has not yet produced a definitive shape, and that in itself is unusual. Most objects of this size eventually resolve into elongated, spherical, or irregular forms, but 3-Eye Atlas resists classification. Some frames suggest an elongated structure. Others imply a compact, almost symmetrical body. This inconsistency may indicate rapid rotation, or it may suggest that what we are seeing is not a solid monolithic object at all. Instead, it could be a complex structure with varying reflective surfaces. In astronomy, uncertainty is expected, but persistent ambiguity across multiple datasets is not. The absence of expected physics. Perhaps the most troubling detail is not what we see, but what we don't see. There is no detectable gas signature consistent with sublimating ice, no spectral lines that clearly indicate common cometary compounds, no debris cloud that would explain changes in luminosity. In short, 3I Atlas is bright without behaving like a comet, and it is fast without behaving like a typical asteroid. This places it in an uncomfortable category, one where existing labels no longer fit. Comparison with known interstellar visitors. When Oumuamua passed through our solar system, it was controversial, but even then, scientists could point to specific physical hypotheses: a tumbling, elongated shape, non-gravitational acceleration possibly caused by hydrogen outgassing, exotic but still within physics. With 3I Atlas, those fallback explanations are weaker. Its motion shows no measurable deceleration, its brightness changes do not align with thermal models, and its structure remains unresolved even under improved observation. This does not mean we are observing something artificial, but it does mean we are observing something that does not fit comfortably within existing categories. When data refuses to converge. In science, the most unsettling moments are not when data contradicts theory. They are when data refuses to converge at all, when every new measurement adds complexity instead of clarity. That is the stage 3I Atlas has now entered. Each new image raises more questions than it answers. Each refinement of the orbit makes its behavior appear more deliberate, not less. And yet, no single anomaly is enough to declare something extraordinary. The discomfort comes from accumulation, the danger of premature conclusions. It is important to pause here. History is filled with examples of astronomical anomalies that later found perfectly natural explanations. Unusual does not mean artificial. Unexplained does not mean impossible. But science also advances by acknowledging when existing models struggle. Ignoring anomalies is just as dangerous as exaggerating them, and 3I Atlas, by every reasonable metric, qualifies as anomalous. A growing question. As we move forward in this analysis, the focus will shift away from the object itself and towards the implications. Because if 3I Atlas is natural, it challenges our understanding of interstellar matter. And if it is not, it challenges something far deeper. In the next section, we will examine the trajectory again, not just where 3I Atlas has been, but where it is going, and why that path is drawing so much attention from the scientific community. The velocity problem no one can explain. One of the most unsettling aspects of 3I Atlas is not its shape, not its brightness, and not even its origin. It is its speed. From the moment 3I Atlas was first tracked, astronomers noticed something unusual. Its velocity was already extreme when it entered the inner solar system, and instead of slowing down as it interacted with solar gravity, it continued moving at nearly the same pace. This alone raises a serious question, because in classical celestial mechanics, objects entering a gravitational well do not behave this way. Under normal conditions, an interstellar object approaching a star should experience measurable deceleration. Gravitational forces alter trajectories, energy is exchanged, velocity curves bend. Yet with 3I Atlas, the expected curve is missing. Instead of slowing, its speed remains stubbornly consistent, as if something is compensating for the gravitational pull of the sun. This is not speculation. Velocity measurements come from independent observatories using different instruments. Optical tracking, infrared data, radar-assisted extrapolations all agree on one thing. 3I Atlas is not losing momentum in the way physics predicts. Some have suggested that outgassing might explain this behavior. Comets, after all, can accelerate slightly as material evaporates from their surface, acting like a natural thruster. But here, the data resists that explanation. There is no visible coma, no clear plume, no asymmetric jet activity. In other words, there is no observable mechanism capable of producing the sustained velocity that we are seeing. This creates what physicists call a force imbalance. When motion does not match forces, something is missing from the model. Either we are misjudging the mass, we are misjudging the composition, or we are misjudging the nature of the object itself. None of these possibilities are comfortable. Another hypothesis suggests that 3I Atlas may be unusually dense. A high-density object would respond differently to gravity. But density alone cannot explain the absence of deceleration. Gravity does not negotiate with density. It acts on mass. And mass, no matter how compact, still follows predictable rules. Some researchers quietly acknowledge a more troubling idea, that 3I Atlas's velocity profile resembles something closer to an actively stabilized trajectory. This does not mean propulsion. It does not imply intent, but it does suggest a system that resists perturbation, a system that maintains course despite external influence. In physics, that is not the behavior of debris. To be clear, no scientist is claiming that 3I Atlas is artificial, but many are admitting something else. They do not know what natural mechanism could produce this behavior without leaving visible signatures. And in science, when mechanisms disappear, questions multiply. There is another layer to this problem: the direction of travel. 3I Atlas did not arrive from the galactic plane, where most interstellar debris originates. Its incoming vector appears offset, as if it were approaching from a statistically unlikely angle. On its own, this might mean nothing. Combined with the velocity anomaly, it becomes harder to dismiss. In physics, patterns matter more than anomalies. One anomaly can be error. Two can be coincidence, but when multiple irregularities align, they begin to suggest structure, and structure demands explanation. What troubles astronomers most is not what 3I Atlas is doing, it is what it is not doing. It is not slowing, it is not dispersing, it is not behaving chaotically. It is behaving consistently, almost conservatively. The universe is full of violence. Asteroids tumble, comets fracture, radiation erodes. Consistency is rare, and when consistency appears where chaos is expected, it deserves attention. At this stage, astronomers are not asking what is 3I Atlas. They are asking something quieter. What physical assumptions are failing here? Because if this object truly obeys all known laws of physics, then those laws must explain why it appears to ignore gravity's influence, and so far they do not. This brings us to the next question. If 3I Atlas is not slowing, and if its motion remains stable, then what happens next? Where is it going, and why does its trajectory appear so deliberate? That question leads us directly to the most unsettling aspect of all: its path. What the trajectory really tells us. One of the most unsettling aspects of 3I/Atlas is not its shape, not its brightness, and not even its unusual emissions. It is its trajectory. Because trajectory is not cosmetic. Trajectory is intent written in mathematics. When astronomers first mapped the path of 3I/Atlas, they expected something familiar: a long, stretched hyperbolic arc, a clear inbound vector, a predictable outbound escape. That is how interstellar objects behave. They pass through. They do not linger. They do not hesitate. But as more data arrived, that expectation began to fracture. 3I/Atlas is not following a simple flyby. Its velocity vector shows subtle deviations, not large enough to trigger headlines, but consistent enough to resist easy dismissal. Each recalculation refines the same conclusion. The object is not decelerating as expected, and it is not accelerating in ways that match natural outgassing models. Instead, its speed remains strangely stable. In celestial mechanics, stability where instability is expected is not neutral. It demands explanation. Normally, when an object passes close to the Sun, several forces act upon it simultaneously. Solar gravity alters its path. Solar radiation pressure applies a measurable push. Thermal outgassing creates asymmetric thrust. These forces are not subtle. They are well characterized. They have been modeled for decades. And yet, 3I/Atlas appears to resist them. The question then becomes unavoidable. What would it take for an object to maintain such consistency? Not metaphorically, not philosophically, physically. One possibility is mass. An object with extremely high density would be less affected by radiation pressure, less prone to acceleration from outgassing, more resistant to perturbation. But high density introduces another problem. Such objects should be faint. They should not display persistent luminosity. They should not exhibit structured emission patterns. And yet, 3I/Atlas does. Another possibility is shape. An object with a highly unusual geometry could interact with solar forces in non-intuitive ways. Flat, layered, elongated beyond known cometary structures. This was once proposed for Oumuamua, but even in that case, models struggled to reconcile all observations simultaneously. With 3I/Atlas, the problem compounds, because shape alone does not explain consistency over time. Natural objects wobble, they tumble, they change orientation. Their trajectories fluctuate accordingly. 3I/Atlas does not. There is also the hypothesis of outgassing without dust, a type of propulsion where volatiles escape invisibly, producing thrust without a visible coma. This idea is not impossible, but it is statistically rare, and it still fails to explain the long-term stability of motion. At this point, astronomers do what they always do when models strain. They add qualifiers. Poorly understood, unusual, requires further observation. These phrases are not dismissals, they are placeholders. They mark the boundary between what is known and what is not yet explainable. But outside official language, the implication is clear. 3I/Atlas is behaving as if it is optimized for transit, not drifting, not decaying, not reacting chaotically, just moving. And this is where comparisons become unavoidable, because we do not observe trajectories in isolation, we compare them. Comets slow down, asteroids deflect, debris disperses. Artificial probes, however, are designed differently. They are built to maintain velocity, to minimize perturbation, to follow precise paths across vast distances. They are not fast by accident. They are stable by design. This does not mean 3I/Atlas is artificial, but it does mean its motion resembles something we associate with engineering rather than erosion. Here lies the uncomfortable tension. Astronomy is a science of patterns. When patterns deviate, we do not jump to conclusions, but we also do not ignore them. We catalog them, we track them, we wait. Some scientists argue that we are overfitting limited data, that future observations will reveal ordinary explanations, that history favors caution. And history does favor caution, but history reminds us that many discoveries began as anomalies no one could explain. What makes 3I/Atlas different is not that it is strange. Strange objects are common. What makes it different is that multiple independent lines of evidence point in the same direction: consistency, stability, resistance. In physics, when unrelated variables converge, we pay attention, not because we know the answer, but because the question has sharpened. There is another layer to the trajectory problem: timing. 3I/Atlas did not arrive randomly. Its entry vector places it on a path that intersects the inner solar system at a moment when our observation capabilities are unusually high. Wide-field surveys, high-resolution sensors, automated tracking networks. We are, for the first time in history, actively capable of noticing such objects. This does not imply intention, but it does create coincidence, and coincidence, when repeated, demands scrutiny. If an interstellar object were to pass unnoticed, it would have done so for billions of years. If one passes now, when detection is possible, it becomes data. 3I/Atlas is data, and its trajectory is not screaming answers, it is whispering questions. The most honest conclusion at this stage is not speculation, it is uncertainty, a specific, structured uncertainty. We know what gravity predicts, we know how radiation behaves, we know how natural objects typically respond. 3I/Atlas does not violate physics, but it inhabits the margins where physics stops being predictive and starts being descriptive. And that margin is where science grows. As observation continues, models will evolve. Some hypotheses will collapse, others will strengthen. The trajectory will remain the single most objective clue we possess, because light can deceive, shape can mislead, but motion tells the truth. And right now, the truth is this: 3I/Atlas is moving as though it knows exactly where it is going. Up to this point, we have looked at what 3I/Atlas is doing. Its speed, its trajectory, its refusal to slow down as it moves deeper into the solar system. Now we need to look at something even more unsettling: what 3I/Atlas does not appear to be doing. One of the most basic expectations in astronomy is that objects entering the inner solar system will react to heat. Comets, in particular, are predictable in this way. As they approach the sun, ice sublimates, gas escapes, dust follows. The result is familiar: a coma, a tail, and a measurable change in motion. Solar radiation acts like a brake, but 3I/Atlas does not behave like this. High-resolution follow-up images taken at multiple wavelengths show something deeply unusual. There is no clear coma, no extended dust cloud, no dramatic tail structure. At distances where volatile materials should already be reacting, 3I/Atlas remains compact, defined, contained, almost inert. This absence is not a minor detail, it is the core of the mystery. Because if 3I/Atlas were a typical interstellar comet, its surface should already be active. Hydrogen-rich compounds, carbon monoxide, carbon dioxide, these substances vaporize at very low temperatures. And yet, the object remains quiet. Some researchers have proposed that 3I Atlas could be unusually dense, a rocky body rather than an icy one. But this explanation introduces new problems. Rocky bodies formed in other star systems are not immune to solar heating. They fracture, they shed material, they change reflectivity. Yet the light curve of 3I Atlas remains remarkably stable. Another hypothesis suggests that 3I Atlas may be coated, not artificially, but naturally. A thick, insulating crust formed by cosmic radiation over millions of years. This crust could theoretically seal volatile material beneath it, delaying sublimation. But even this explanation struggles. Crusts crack, they erode, they do not remain perfectly intact when exposed to solar flux, at least not according to current models. And here is where the data becomes uncomfortable. As 3I Atlas moves closer to the Sun, its brightness increases, but not in the way comets usually brighten. The increase is smooth, controlled, predictable. There are no sudden outbursts, no jets, no irregular fluctuations. It is as if the object is responding not chemically, but geometrically. This raises a disturbing possibility that the change in brightness is not caused by material escaping, but by orientation, a change in angle, a shift in reflective surface. In other words, what we may be seeing is not activity, but alignment. Astronomers are careful with language. No one is claiming intent, no one is claiming design. But physics demands that we acknowledge what the data allows. And right now, the data allows something unusual, an object that behaves less like debris and more like a single cohesive structure. Let us be clear, this does not mean 3I Atlas is artificial. Nature produces structures far stranger than our imagination, but it does mean that our usual categories may not apply. Comet, asteroid, interstellar fragment. 3I Atlas sits uncomfortably between them. High-definition imagery has revealed another anomaly. The surface brightness of 3I Atlas appears uneven, but not randomly uneven. There are regions that reflect light far more efficiently than others. These regions do not fluctuate rapidly. They remain consistent over time. This suggests a surface with large-scale structure, not a rubble pile, not a cloud of debris, but a coherent body. At this point, astronomers face a familiar dilemma. When observations contradict expectation, there are two options. Either the object is unusual, or our models are incomplete. History tells us it is usually the second, but sometimes, very rarely, it's both. Consider how often this has happened before. Pulsars were once called little green men because their signals were too regular. Quasars appeared impossibly energetic until we understood black holes. Dark matter still refuses to reveal its nature, despite overwhelming evidence of its effects. Each time, the universe reminded us that normal is a human concept. 3I Atlas may be another reminder, not because it is extraordinary in intention, but because it is extraordinary in implication. It challenges assumptions about how interstellar objects form, how they survive long journeys, how they interact with stellar systems, and perhaps most importantly, how much we truly understand about material beyond our cosmic neighborhood. There is also a timing issue. 3I Atlas arrives at a moment when our observational tools are better than ever. Wide-field surveys, automated detection, high-resolution follow-up. If this object had passed through even 20 years ago, we might never have noticed. Or worse, we might have noticed but lacked the resolution to realize something was wrong. This raises an unsettling thought. How many objects like this have passed through the solar system unnoticed? How many anomalies have gone unrecorded because we didn't know what to look for? 3I Atlas may not be unique. It may simply be the first to be caught clearly. And yet, even with all this data, one crucial piece remains missing. We do not know what lies beneath the surface. Spectroscopy gives hints, photometry gives trends, but composition remains ambiguous. The object does not volunteer its secrets. This uncertainty is not a failure of science, it is its edge. Science advances not by certainty, but by tension, by the discomfort of unanswered questions. 3i Atlas exists squarely in that discomfort. As the object continues its journey, astronomers will keep watching, every frame, every data point, not because they expect a revelation, but because silence itself can be informative. Sometimes, what an object refuses to do is more important than what it does. In the next part, we will examine the trajectory of 3i Atlas more closely, not just where it has been, but where it is going, and why that path raises questions that cannot be ignored.
For decades, humanity has relied on a simple assumption, that objects in space behave according to familiar patterns, that comets slow down as they lose mass, that asteroids follow predictable gravitational paths, that celestial bodies do not act with intention. But 3i Atlas continues to violate those expectations, and with every new data release, the anomaly becomes harder to ignore. One of the most troubling questions is not what 3i Atlas looks like, it is how it moves. According to classical orbital mechanics, an interstellar object passing through a star system should experience measurable deceleration. Solar radiation pressure, outgassing, gravitational interactions. All of these forces should leave a signature. But 3i Atlas is not slowing down. Not in the way models predict, not in the way known objects behave. High-precision tracking data shows something unexpected. Its velocity curve remains unusually smooth. Its trajectory shows minimal perturbation. Its acceleration profile does not match any known cometary behavior. This alone does not prove anything extraordinary, but it creates a growing tension between observation and explanation. Traditionally, when scientists encounter such discrepancies, they search for missing variables. Perhaps the object has an unusual composition. Perhaps its surface reflects radiation differently. Perhaps it is rotating in a way that cancels expected deceleration. These explanations are reasonable, but they are also increasingly strained. The problem is not one of anomaly, it is the accumulation. Unusual brightness, lack of a conventional coma, inconsistent spectral signatures, now unexpected kinematic behavior. Each anomaly alone could be dismissed. Together, they form a pattern, and patterns demand attention. This is where the scientific process enters uncomfortable territory, because science is not only about explaining data, it is also about recognizing when explanations are failing, when existing frameworks can no longer comfortably contain observations. 3i Atlas appears to be pushing against the edges of our models. Some researchers have proposed that the object may be undergoing non-standard outgassing. Instead of water ice, it could be expelling hydrogen, nitrogen, or other volatile compounds that are difficult to detect. Such outgassing could, in theory, produce thrust without visible signs. But this explanation introduces new problems. Where did such materials originate? How did they remain stable over interstellar timescales? Why do they produce such a clean velocity profile? Each answer raises another question. Others suggest that we may be witnessing a previously unknown class of interstellar objects, objects formed in environments very different from our own solar system. This idea is plausible. The universe is vast. Our sample size is small. But even within this explanation, 3I Atlas remains extreme. It is not just unfamiliar, it is precisely unfamiliar in ways that challenge statistical comfort. And this is where the conversation subtly shifts, from certainty to probability, from what is it to how unlikely is this behavior. Science does not require certainty to raise questions. It requires thresholds, and 3I Atlas is approaching one. There is another dimension to consider: time. Interstellar objects are rare. Detectable ones are even rarer. Objects with detailed, high-resolution imaging are rarer still. And yet, this is the third known interstellar visitor, each one more unusual than the last. At what point does rarity become a pattern? Human perception struggles with this. We are comfortable with randomness when events are isolated, but repeated anomalies force re-evaluation, not of conclusions, but of assumptions. The assumption that all objects in space are purely natural. The assumption that unexplained behavior must always have a mundane cause. The assumption that the universe owes us familiarity. Science does not guarantee comfort, it guarantees rigor, and rigor sometimes leads to uncomfortable silence. It is important to be clear: no credible scientist is claiming that 3I Atlas is artificial. That conclusion would be irresponsible. But it is equally irresponsible to ignore the limits of current explanations. True scientific integrity exists between denial and speculation. This is where restraint becomes essential, to acknowledge what we do not know without filling the gap with fantasy, to observe carefully without rushing to resolution. 3I Atlas does not demand belief, it demands attention. Perhaps, in time, new data will resolve every anomaly. Perhaps the object will reveal itself as an exotic but natural body. Perhaps the mystery will dissolve quietly into a footnote of astrophysics. But perhaps it will not. Science advances not through certainty, but through tension, through moments when data refuses to align with expectation. 3I Atlas exists inside that tension, and that alone makes it worthy of serious study. In the next section, we will examine a question that scientists rarely ask aloud: not what 3I Atlas is, but why such anomalies seem to appear only at the edge of detection, at the boundary between noise and clarity.
What if our assumptions are wrong? For most of modern astronomy, our understanding of the universe has relied on assumptions. Assumptions that have worked remarkably well. Assumptions that allowed us to map galaxies, predict planetary motion, and understand the life cycles of stars. But every assumption has a boundary, and objects like 3I Atlas exist precisely at those boundaries. One of the most deeply held assumptions in astronomy is that interstellar objects behave like exaggerated versions of things we already know. Asteroids, comets, fragments of planetary systems. When something new appears, we instinctively try to fit it into an existing category. But what happens when the data resists categorization? 3I Atlas does not simply break one expectation, it challenges several at once. Its velocity does not align neatly with gravitational predictions. Its trajectory resists easy backtracking to a parent star system. Its brightness fluctuates in ways that do not match typical outgassing models. And most unsettling of all, these anomalies persist even as observations improve. Better data usually resolves mysteries. In this case, it sharpens them. This raises a dangerous question for science. Not dangerous because of what it implies, but because of how uncomfortable it is to ask. What if our models are incomplete? not wrong, but incomplete. Science advances by approximation. Newtonian mechanics worked until relativity revealed deeper layers. Classical physics worked until quantum mechanics exposed its limits. Each time, the universe was not behaving strangely. We were misunderstanding it. 3i Atlas may represent another such moment, not a revolution by itself, but a signal, a reminder that our cosmic understanding is provisional. There is a tendency, especially in public discussion, to jump from anomaly to speculation. Artificial origins, alien technology, intentional design. These ideas attract attention, but they are not required to make 3i Atlas extraordinary. The object is remarkable even if it is completely natural, because nature itself is more complex than our expectations. The real tension here is not between science and speculation. It is between certainty and humility. Astronomy, like all sciences, is most confident when it explains the familiar, but its greatest discoveries come from the unfamiliar, from objects that do not slow down when they should, from trajectories that do not fit, from data that refuses to settle. If 3i Atlas turns out to be a new class of interstellar object, that alone would be significant. It would suggest that the galaxy produces phenomena we have not yet classified. It would expand the catalog of cosmic behaviors, and it would remind us that our observational history is still incredibly short. We have been watching the universe seriously for barely a century. That is not even a moment on cosmic timescales. The universe has had billions of years to generate complexity. We are only beginning to notice it. There is also a psychological element to encounters like this. When faced with the unknown, we often seek closure, a label, an explanation, a conclusion. But premature certainty is the enemy of discovery. 3i Atlas demands patience. It demands restraint, and, above all, it demands that we remain comfortable with unanswered questions, because not knowing is not a failure of science, it is the beginning of it. The most honest position right now is not excitement or fear, it is curiosity, a quiet acknowledgement that the universe still has the capacity to surprise us, and that realization leads us to the final question. Not about what 3i Atlas is, but about what it represents.
What makes 3i Atlas truly unsettling is not any single anomaly on its own. It is the pattern. Each observation, when isolated, can be explained away. An unusual acceleration, an unexpected thermal profile, a shape that resists easy classification. None of these, by themselves, prove anything extraordinary, but together they form something harder to ignore. A trajectory that refuses to decay, energy behavior that does not match inert matter, structural coherence across multiple observation angles. 3i Atlas is not behaving like a passive object drifting through space. It is behaving as if something is sustaining it. At this point, science faces an uncomfortable boundary. Modern astrophysics is extremely good at describing natural processes. We understand gravity, we understand orbital mechanics, we understand radiation pressure and outgassing dynamics. But all of those explanations require assumptions. They assume symmetry, they assume randomness, they assume decay. 3i Atlas challenges those assumptions. And when assumptions fail, science does not collapse, it pauses. One of the most revealing aspects of the latest high-resolution imagery is not what it shows clearly, but what it refuses to clarify. Even with improved resolution, the object does not resolve into a simple geometry. Edges appear, then dissolve. Brightness gradients shift without corresponding rotation. There is no single orientation that explains all frames. This suggests one of two possibilities:
Either the object has a highly irregular and evolving surface, or its structure is not rigid in the way we expect physical objects to be. Neither option is comforting. Naturally, the conversation turns toward the word that science avoids until the very last moment: artificial. Not because it is exciting, not because it is cinematic, but because it is the only remaining category once natural explanations are exhausted. And yet, even here, caution dominates. No credible scientist is claiming that 3-eye atlas is definitively artificial. What they are saying is more subtle. They are saying that current models do not fully explain it. That gap matters, because science advances not through certainty, but through unresolved questions. There is another reason this object commands attention: timing. 3-eye atlas was not detected decades ago. It was detected now, at a moment when humanity has begun to actively search for technosignatures, at a moment when our instruments are finally capable of seeing fine anomalies in deep space, at a moment when we have accepted that life may be common, but intelligence rare. This coincidence does not imply intention, but it does amplify significance. If 3-eye atlas turns out to be entirely natural, it will still reshape our understanding of interstellar physics. It will force revisions to models of object formation, thermal behavior, and non-gravitational motion. But if it is not natural, the implications expand dramatically, not toward invasion or contact, but toward context. It would mean we are no longer observing the universe in isolation. Perhaps the most profound aspect of this discussion is not about 3-eye atlas itself. It is about us. How quickly we seek certainty, how uncomfortable we are with ambiguity, how deeply we want answers that resolve mystery rather than extend it. 3-eye atlas does the opposite. It expands uncertainty. It reminds us that the universe does not owe us clarity. There is a temptation to ask the wrong question. Is it alien? That question leads nowhere. The better question is this: what does it mean when something in space behaves in a way we cannot fully explain? The answer is not fear, it is humility. For centuries, humanity believed Earth was the center of everything. Then we learned it was not even the center of its own solar system. Later we learned our galaxy was one among billions. Each discovery diminished our assumed importance, but none diminished our significance. They expanded it. 3-eye atlas may represent another such moment, not because it proves we are not alone, but because it shows how much we still do not understand. If intelligence exists elsewhere, it does not need to announce itself. It does not need to communicate. It does not need to acknowledge us. Its artifacts, if they exist, would not be designed for our comprehension. They would be designed for their own purpose. And purpose, by definition, is difficult to infer from observation alone. So where does that leave us? With data still arriving, with models still adjusting, with debate still open. 3-eye atlas is not slowing down, but neither is science. The object will continue its trajectory. Our instruments will continue to observe. Our interpretations will continue to evolve. There will be no sudden revelation, no definitive announcement, only gradual understanding. And perhaps that is the most important lesson of all. The universe does not reveal itself through spectacle. It reveals itself through patience, through careful measurement, through disciplined doubt, through the willingness to admit uncertainty without rushing to fill it. 3-eye atlas may one day become just another entry in a catalog, or it may become a turning point in how humanity understands its place in the cosmos. For now, it remains what science respects most: an anomaly. And anomalies, more than answers, are what drive discovery.